land surface is the third component, the third reservoir of Earth's carbon cycle. So the difference between the land surface and the solid Earth is the land surface is kind of just the carbon that's exposed at the surface, which can respond sort of quickly, as opposed to the solid Earth, I mean stuff that's buried for millions of years. So the land carbon cycle is governed by plants mostly. Plants grow in the spring and summer, and they take up CO2. And then in the fall and in the winter, they drop their leaves, which decompose or turn back into CO2 and released back to the atmosphere. So there's a very strong seasonal cycle in the CO2 concentration of the atmosphere, which is driven by the land surface. It goes up in the winter and down in the summer. You can see that in the southern hemisphere, the seasonal cycle is much less intense in CO2 because there's less land in the southern hemisphere. So you have much wider swings of atmospheric CO2 concentration in the northern hemisphere. In the southern hemisphere, they're out of phase with the north because the seasons are out of phase. And then on top of the seasonal cycles from those two regions, you can also see the secular trend, the rise in the CO2 concentration with time, which is due to fossil fuels. So there are a couple of ways that the land biosphere can affect the CO2 concentrations with the fossil fuel CO2 and all. One is deforestation. So if you go from a forested landscape and then you cut down the trees and make an agricultural landscape, you have less carbon per square meter of area in this land after it's been cut than you had before. So that actually provides a net source of carbon to the atmosphere. It's not as much carbon as our fossil fuel carbon, but it's a significant amount of carbon released to the atmosphere. Something else that's going on that's sort of more mysterious is that in places where there's not active deforestation going on, there appears to be a natural uptake of carbon by the terrestrial biosphere. They call greening. And it's not clear what's driving this. It could be that with the climate change we've experienced already, the longer growing season is allowing more plants to grow, or maybe it's allowing area that used to be sort of low carbon tundra to convert into higher carbon forests. It could be actually CO2 fertilization effect. Plants actually grow better if there's more CO2. That's one of the purposes of a greenhouse, is to have higher CO2 concentration. It makes the plants grow better. It could be fire suppression. Actually, it's not even known. Even though there's a fairly large amount of carbon going into the natural landscape someplace, we can't really find it for sure. Don't know where it is. So the landscape is serving as a negative feedback today because it's taking up carbon that we are releasing to the atmosphere. So it's stabilizing the climate and acting as a negative feedback. However, if you look at this map of the distribution of soil carbon on Earth, what you see is that there's much more soil carbon in the high latitudes than there is in the low latitudes. So rainforests look like very carbon-rich, lush places, and there is a lot of carbon in rainforests, but not in the soils. The soils in rainforests are sort of bleached out. There's no carbon really there. It's because a leaf that falls to the ground in the tropics decomposes so quickly, it doesn't accumulate in the soils. Whereas in cooler climates, you have a buildup of more carbon in the soils. And the end-member case is in the very high latitudes in the permafrost regions, the soil is actually frozen, and so the carbon is very well preserved there. You can find intact mammoths from thousands of years ago that are still frozen and even approaching edible after all those years because it's been preserved by freezing. So if on the time scale of centuries we melt that permafrost and go and create a sort of more tropical sort of climate in the higher latitudes, that could result in the net release of a considerable amount of carbon. So again, the land biosphere, like the ocean, has the potential to switch from being a negative feedback that's stabilizing and saving us from ourselves today to being an amplifying positive feedback in the fullness of time in the future. So you've heard about the carbon cycle as a series of reservoirs, all of which inhale and exhale carbon dioxide to the atmosphere, which is sort of the center of the carbon cycle in some ways. But there's another trick that the carbon cycle has done on Earth, which involves this chemical reaction. CO2 plus water combined with energy can be put together into a molecule of the sort of family of CH2O, which is a very, very simple representation of what chemists call organic carbon. So organic carbon is what plants and people and things like that are made out of. And originally, organic carbon could only be made by life, which is why it's called organic carbon. Nowadays, if you go to the grocery store and you buy some organic, fruit or something like that, what it means is that they didn't use any industrial chemicals to produce it. But actually, a lot of those industrial chemicals, like pesticides, can actually be made out of carbon in this sort of configuration that a chemist would actually call organic carbon. So there's different uses for the word organic that actually can be in conflict with each other in different situations. So it takes energy to do this chemical reaction to make organic carbon out of CO2. And where the energy comes from is from light to power photosynthesis. So it takes plants to do this chemical reaction. The other chemical on this side of the equation is oxygen. So this is O2, just like the oxygen in our atmosphere. So it turns out that when organic carbon is buried in the earth, it leaves behind the oxygen that it produced, and this is where the oxygen in the atmosphere comes from. Actually, most of the organic carbon that's produced by photosynthesis is respired back to CO2 because somebody eats it. If we eat our lunch, we are doing respiration, or if bacteria degrade a leaf in the soil or something like that, it sends it back this way. But in very special conditions, this organic carbon can be protected from being eaten by being buried in the mud in the bottom of the ocean or in a swamp or something like that, in which case it leaves behind oxygen in the atmosphere. So what's happened is that the biosphere, the life on Earth, has charged up the surface of the Earth like a giant battery. And we are creatures of this battery. We eat organic carbon and we breathe oxygen in order to have everything we need on this side of the reaction to do respiration, which is how we get energy back. So there are really two reasons why life does photosynthesis. One is to store energy in this form of organic carbon, and another is to put carbon in a chemical state where it has lots and lots of versatility to do all the different things that need to be done in the biomolecular machinery. So the amazing thing about this battery of the biosphere is that it's so remarkably stable. There's no simple chemical reason why we have 20% O2 in the atmosphere instead of 10 times as much or 10 times less. It's kind of an accident of how much of this organic carbon has gotten buried in the mud, in the earth. So it'd be very easy for this system, it seems like conceptually, to have built up to 10 times more oxygen in the atmosphere, in which case a spark of lightning could start a continent-wide forest fire. No wet wood would burn, so nothing could put it out. Or having 10 times less oxygen in the atmosphere, in which case all of us multicellular types would choke and die. And we know that for the last more than 500 million years, there has been multicellular life on Earth. And so the oxygen concentration in the atmosphere is somehow sort of regulated in a very miraculous sort of way. It's got to be something like if oxygen in the atmosphere gets too low, then you get anoxic conditions in the ocean, which make it easier to bury organic carbon, which then acts as an extra source of oxygen to the atmosphere. But scientists don't understand this very well, this uncanny, this eerie stability of Earth's biosphere. To understand how organic carbon saves energy, stores energy, we have to know something about what's called the oxidation and reduction of the carbon. So there are some simple rules. When you put together a molecule that has an oxygen in it, that oxygen is greedy for 2 electrons in the chemical bond. It pulls them very tightly towards itself. Those electrons have a negative charge, and so this oxygen has what's called an oxidation state of -2, equal to the -2 charge of those 2 electrons that it's pulling close to itself. Hydrogen, in contrast, is very generous with 1 electron when it forms a chemical bond. So hydrogen in, say, water, where it's bonded with oxygen, will have a deficit of 1 electron, and so that means that it has an oxidation state, kind of like a charge, of +1. However, there's an exception to this. If you have 2 identical atoms together in a bond, like O2, 2 oxygens are the same as each other, in that case, they have to share equally. So in that case, the oxidation state of those oxygens is each equal to 0. And then the other thing you got to know is that the sum of the oxidation states of all of the atoms in a molecule has to equal the charge in the molecule. So using these simple rules, we can look at the various forms of carbon that we're talking about and understand how its oxidation state changes when the photosynthesis reaction happens. And this is how the energy is stored. You can sort of understand the energy storage by looking at this bookkeeping of electrons. So the most oxidized form of carbon is CO2. So each oxygen here has a -2 oxidation state because each oxygen is greedy for those 2 electrons. And there are 2 of them. So there's a total of -4 oxidation state in those oxygens. The total charge on CO2 is 0. So carbon has to fill in the gap, and it has to have an oxidation state of +4 in order to make this work. Methane, CH4, is the most reduced of the carbon species. That's because each hydrogen that it's bonded to is donating 1 electron. So that's a charge on the hydrogen of +1, and there are 4 hydrogens. So then the carbon has to be -4 in order to have the overall charge on the molecule be 0. So going from CO2, the oxidation state of carbon is +4. Here it's -4. So the word oxidation kind of makes sense just by looking at where the oxygens are. Carbon, CO2 is oxidized carbon. Oxidized iron is rust, which is an iron oxide. So that sort of makes sense. But if you didn't know about the electrons, you wouldn't make any sense out of the word reduced. But the word reduced comes from the oxidation state on the carbon. This number is reduced relative to that one. So this is a reduced carbon atom. CH2 is actually right in the middle of these 2. It's sort of halfway between the oxidized and the reduced ends of the spectrum. So oxygen has a charge of -2. There's 2 positive charges on the hydrogens, and so the oxidation state of this carbon here is 0. Now the reason why we're doing all of this is because the oxidized form of carbon is the lowest energy form of carbon if you have oxygen around. So carbon in CO2 is like a dead battery. You couldn't get any energy out of it because it's already dead. The more reduced the carbon gets, the more energy it's storing. So this will be important for fossil fuels, which we'll learn about next, because some fossil fuels are more reduced, like natural gas is methane. It's very reduced. Oil is sort of in between, and coal is sort of about here. So there's different amounts of energy per carbon in the different types of fossil fuels because of the different oxidation states of the carbon. You can also see why the different fossil fuels yield different amounts of energy just by looking at the reaction of combustion. So coal is mostly just elemental carbon, and it combines with O2 to make CO2. So this is the formation of the CO2 is what yields the energy. Organic carbon is the same oxidation state as coal, but it's got hydrogens and oxygens in it. The H2 and the O here sort of balance each other in the oxidation state because this is it's pulling 2 electrons closer, and the 2 hydrogens are donating 2 electrons. So this part sort of washes. Anyway, when you burn that, you get CO2 plus the water, but there's also water here, so you're not really getting energy from the H2O on the 2 sides there. So this is like coal. You just have this H2O kind of tagging along on both sides, doesn't really affect things. But methane now, CH4, when you combust that, you need more oxygen, and you make this water that didn't exist before. And so the extra energy you get from methane is basically the energy you get from making water.